Alright, let's dive into the world of buffers and buffer capacity. If you've ever wondered how solutions resist changes in pH, you're about to get your answer. The key player here is the buffer equation, better known as the Henderson-Hasselbalch equation. For acid buffers, think of a weak acid, let's call it HA, mixed with its salt, like sodium acetate. The magic starts with the dissociation of HA into H plus and A. The equation looks like this. Ka equals the concentration of H plus times A divided by HA. Now, because weak acids barely dissociate and adding the salt gives you more A ions, we get what's called the common ion effect. This basically keeps the concentration of the unionized acid nearly the same as when you started. Since the salt dissociates completely, its concentration gives you the A value in the equation. Crunching the math and taking the log of both sides leads us to the Henderson-Hasselbalch equation, pH equals pKa plus the log of salt over acid. This lets me calculate the pH of any acid buffer as long as I know my concentrations. For basic buffers, it's the same idea, just flipped. Take a weak base, BOH, and its salt, Ba. BOH dissociates into B plus and O. The salt gives you more B plus ions, and the buffer equation becomes POH equals pKb plus log of salt over base. Now let's talk buffer capacity. Buffer capacity, symbolized as beta, measures how much acid or base I can add before the pH really starts to shift. It's calculated as the amount of acid or base added divided by the change in pH. The higher the buffer capacity, the better the solution resists pH changes. Add acid or base, and if the pH barely budges, that's a high buffer capacity at work. So next time you're mixing up a buffer, remember, it's all about the balance and the math.